For question 3, right, we have this particular Nobel-winning work by Barry Sharpless. Okay, so it is for his breakthrough in asymmetric oxidation. Yeah, he is using this particular complex, titanium complex, known as this titanium complex, okay, with a chiral diisopropyl tartrates, okay, and then of course the subsequent oxidizing agent is tertiary butyl hydroperoxide. Yeah, so this is just represented by DIPT in short. Okay, so whether it take on plus or minus. Yeah, so if it approaches from the top, then it's going to deliver oxygen on the top of this cartoon or this particular diagram. Yeah, so if it approaches from the bottom, then it will approach it, it will insert oxygen onto the bottom. Yeah. So now the question is, when S undergoes the reaction above, with an unknown configuration, epoxide T is obtained in the reaction scheme below. You are asked to suggest the configuration of DIPT used. So basically your answer is either plus DIPT or minus. Okay, so it's a 50-50% chance of getting correct. Yeah, because it's a 50-50% chance, as you know, most of the time, we don't give credits to guesswork, so you have to explain how you obtain your answer. Okay, so how do we obtain our answer? I think first of all, we need to fit S into the cartoon above. Yeah. So how do we fit S into the cartoon above? So first we will do a bond rotation. Sorry, not bond rotation. We'll rotate the molecule 90 degrees. Yeah, so we just rotate 90 degrees. Okay, so when we rotate it 90 degrees, it will look like this, and then like this, and then like this, like this, and then like this. Okay. Oh, sorry. So the top is it's actually a H. Yeah. So like this. So this is how it looks like when we rotate it 90 degrees. Okay. So 90 degrees. Oh, sorry. Carbon 2 have another bond. Yeah. So we'll rotate it 90 degrees. This is how it looks like. But you'll notice that if I compare between the structure I've drawn in blue and the diagram above, right, it doesn't fit. Yeah, because I need to fit the CH2OH into this particular side. So I need to fit it into this side. Yeah, in order for me to predict the correct catalyst. Okay, or rather to predict the catalyst with the correct configuration. Yeah, so in this case, right, in order to fit, I need to do a bond rotation. I need to do a flip. Okay, 180 degrees flip into the plane of the paper. Yeah, so when I do that, I'm going to end up with something like this. Okay, like this, and like this. Okay, so again, this is 2 and this is 1. Yeah, so after doing this, right, now you can see that this essentially is R2. Okay, so this is R1. Okay, and the H here, so there's a H here, which I didn't draw out. So this is essentially R3. Then the next thing I'm going to do is to rotate T as well. Okay, so we'll do the same thing, rotate 90 degrees and then flip it into the plane of the paper. Yeah, so we're going to end up with something like this. I'm going to just draw it out very quickly. We're going to end up with like this, like this, like this, OH, and then so this is carbon 1, this is carbon 2, and then of course the like this, and then like this. Okay, and then of course we have the groups projecting upwards. The epoxy oxygen is now projecting upwards. Yeah, then now I'm going to compare these two, so the structure here as well as the structure here. Yeah, so you notice that because now the epoxy oxygen is pointing upwards, so I should be using plus DIPT. Yeah, so it's as simple as that. Of course, when you explain to the examiner, all you need to do is simply just draw this out, and then if you can, identify R1, R2, and R3, and then point to the examiner that compound T, if you flip it into the same configuration or the same conformation in that sense, you have the epoxy oxygen pointing upwards. So therefore, in order for the epoxy oxygen to be pointing upwards, the DIPT will have to approach from the top, and therefore I should be using plus DIPT instead of minus DIPT. Yeah, so any reasonable explanation will work, right? Then we'll move on to part B. Okay, so now part B, we were told that when epoxides are subjected to sodium hydroxide solution, the epoxide ring will open and a diol will be obtained in the reaction scheme shown below. Okay, so when epoxide T is subjected to sodium hydroxide, two products are possible. One of the products, W, has RS configuration. Okay, so let us take note of this. RS configuration at C1 and C2 respectively. Okay, so now the first thing we need to do is I think we need to redraw T. Yeah, so if I'm going to draw T, right, T will actually look like this. Okay, projecting inwards like this. Okay, one of the mistake, I would say mistake, one of the common thing which most of the students do, right, is they tend to draw the mechanism directly following what we have drawn for you. So a lot of students actually draw the mechanism like this, and then the ring will open, and then what they're going to end up with is something like this, O minus, and then they have something like OH here. Yeah, so there is actually nothing wrong in drawing the mechanism like this, except that it's very difficult to see the rear attack. Yeah, because if you take a look at parts B2, right, question says it's SN2 like fashion. So when they wrote SN2 like, it is really important for the students to recognize that they have to draw a rear attack to the best of their ability, of course. Yeah. Okay, I'm actually jump starting like from I haven't done B1 yet, so I'm just going to just showcase to you that eventually the SN2 mechanism will lead to W and something else, which is another product, because later on you need to suggest how the other products may be obtained. And then of course here you know that I can the hydroxide can either attack carbon 1 or carbon 2. Okay, so carbon 1 is a tertiary carbon, carbon 2 is a secondary carbon. Yeah, so being SN2, hydroxide will prefer to attack carbon 2 rather than carbon 1. Okay, yeah, so in this case I think the easiest way is simply just draw out the mechanism, and then perhaps get the product out first before we do B part 1. Yeah, I thought that would be the easier approach, but if you want, you can simply just draw the product out and then try to predict the configuration, and then if you get the correct configuration, then that will be W. If you get the opposite, then you just swap the relevant stereochemistry around, and then you should be able to get the correct answer for parts 1. Okay, yeah, and then I'm going to introduce you to another method or another perspective for you to draw such mechanism in a slightly more elegant manner. So what you can do is I'm going to show you a different perspective of looking at this particular structure. Okay, so that eventually you end up with a relatively nice staggered configuration as you draw your mechanism. Okay, yeah, so what I'm going to do is I'm going to showcase to you the epoxide taking on the plane of this paper like this. Okay, so this is carbon 1 and this is carbon number 2. Okay, and then because this is carbon number 1, what I'm going to do is the methyl group will now be projecting into the paper, and then the OH, or rather the CH2OH group, will now be projecting out. Okay, and then of course let me see, the H will now be projecting in. Okay, oh sorry, the ethyl group will project in, and then the H will project out. Okay, so I'm going to showcase to you maybe one of the perspective you can take when you draw such mechanism, because if you look at it this way, right, it's easier for you to draw out your mechanism to showcase the rear attack. Okay, then after that, what I'm going to do is I have a hydroxide here. Okay, so I'm going to attack carbon number 2, and then the ring will open. Okay, so when I attack carbon number 2, the ring open, right? I'm going to end up with this OH. Okay, this is carbon number 2, carbon number 1, O minus. Okay, then project in, project out. Okay, and then the H like this, and then like this. Okay, and then of course this will then undergo acid-base neutralization with H2O. Okay, to get the product. So my product, I'm going to find a space to draw. So maybe I'll draw it below here. Okay, I'm just going to draw it below because there's no space. Okay, like this. So I'm going to draw it like this. So this carbon 2, 1, OH, projecting in, projecting out, OH, in and out. Okay, so this is one product. Another potential product I can draw is my hydroxide can now approach from carbon number 1 and then the ring will open. Okay, so I'm not going to draw the intermediate alkoxide. I'm just going to simply draw the final products out like this, like this, like this, OH, and then projecting in, projecting out, OH, and then H here, and then like this. Okay, so this is carbon number 2 and carbon number 1. Okay, so if you try to label the RS configuration over here, yeah, then let's try to do that. So carbon number 2, the H is projecting towards me. Okay, so it's the lowest priority. So the highest priority is the oxygen here. Okay, so this is priority 1, and then the right hand side, this will be priority 2, and then 3, right? So 1, 2, 3 in a clockwise manner. Okay, but because hydrogen is projecting towards me, yeah, so if I look from the back, it will be anti-clockwise. So carbon number 2 will take on the S configuration. Okay, so I'm going to erase this first. Okay, carbon number 2, S configuration. Next, we're going to look at carbon number 1. So O will take on first priority, and then CH3 is likely to be the lowest priority. And then over here, we have CH2OH. So the other one, carbon number 2, will be carbon as well. Yeah, but because they share the same atom, so we're going to need to look at the next level. So the next level will be O, H, H. Okay, and then for carbon number 2, it will be O, C, and H. Yeah, so there's a differentiating one at the second counts. Okay, so in this case, carbon is the differentiating one. Okay, so carbon number 2 will take on a higher priority. So this is second priority. This will be the third priority. Yeah, so lowest priority group pointing away from us, so this will be a clockwise, so we'll take on R configuration. Yeah, so if you take a look at the question, W has R configuration at C1, S configuration at C2. Yeah, so this will be my W. Okay, so yep, we have answer B part 1. So my W is the structure in red. We have also answer B part 2 because we have drawn for you the mechanism giving us W in red, and then of course the other stereoisomers in blue. Okay, then in B part 3 suggests if W is the major products. Briefly explain why. Yeah, so W is not the major products. Yeah, as what we have seen above, because carbon number 1 is the tertiary carbon, carbon number 2 is a secondary carbon. Yeah, so because of that, carbon number 1 is more sterically hindered as compared to carbon number 2. Yeah, so in that case, SN2 will not be preferred at carbon number 1. Yeah, so therefore W is not the major products. Okay, so not the major products. Okay, next for part 4, you are supposed to suggest a suitable starting material to obtain the other diastereomer of T, keeping the reaction conditions configuration the same. So we're going to use plus DIPT. Yeah, so for me to get the other diastereomer, yeah, so that means that instead of maybe we'll make it easier. So I'm going to get this like this, maybe. Oh, yeah, so remember that for diastereomer, only one of the chiral center changes. Yeah, then if I'm going to use the same DIPT, that means that the DIPT must come from the bottom, right? Yeah, but of course, if we fit it into this cartoon, it will come from the top. Yeah, so because of that, then therefore my starting material will look like this. Okay, so this will be the answer. Yeah, so this will be the compound I will use to produce the other diastereomer of T. Yeah, I hope that's okay. Yeah, so this is the simplest and fastest way to come up with the answer. Okay, so that will be the end for question 3.